Okay, calculus folks, here is some questions about area between curves and some volume from rotations. So this first problem says we're rotating this figure along the line y equals 4. So here is your y-axis. So this is volume, right? Volume, we are rotating and we're going to get circles. So this is going to be a disk method problem. So let's think about what is the inner radius and what is our outer radius. So the outer radius goes from your line to your outer function. Okay? So how do we get the maximum radius of this graph? What would the maximum radius of the graph be? The maximum radius is 4. The maximum radius is 4. So all the other radiuses have to be smaller than 4. So this is a subtraction problem. 4 minus what? 4 minus our bottom function. And what's our bottom function? E to the x minus 3 power. So that's how we find the outer radius. You go from your maximum radius minus, right, the y values from your graph. So 4 minus. Now what about our inner function? That's going to go from your line to here. Right, so how do we find each of those lengths? Well, it's the same idea. 4 minus whatever the y value is right here. And how do we find the y value? Well, that's our other function, 2 plus sine x. Okay, so we have to think about what is the maximum radius possible for our graph. Okay, and then go from there. So the maximum radius is going to be 4, and then everything else is smaller than 4. So it's a subtraction. So volume is pi r squared, right, because these are disks. Your outer radius is 4 minus e to the x minus 3 quantity squared minus 4 minus 2 minus sine x quantity squared dx. So that's your radius, right? The outer radius squared minus the inner radius squared. And I guess 4 minus 2, I know what that is. 4 minus 2 is, well, that's just normal 2. So I can do a little bit of simplifying before I plug this into my calculator. But there's one more issue, and that's what are the bounds. Okay, what's the lower bound clearly is going to be 0, but what about this upper bound? Where do our graphs intersect? Well, let's put these two equations into our calculator and see if we can do the intersection. So here's the graph. I see that the graphs intersect when x equals 3.5, so that's going to be the upper bound of my graph. So 3.5 goes as my upper bound. Now it's just a matter of putting this into the calculator. There's your final answer. So that means that our answer is A, 115.380. Okay, number 2. Find the area of the region. So this just says area. Area of the region in the first quadrant enclosed by cosine, y equals x, and the x-axis. So hopefully you know what cosine looks like. Right, cosine starts at a max and comes down to here. So cosine y equals x, which is this line. Right, so we're talking about this area right here. Y equals x and cosine. So once again, the question is, where do these two things intersect? From 0 to where? So area is just the integral of the top equation, which is cosine, minus the bottom equation, right? No squaring, no pies, no radiuses. Area is just the top minus the bottom. So our question is, where do these graphs intersect? What is our upper bound here? Let's go to the graph and figure it out. So it looks like these graphs intersect at 0.7391. Okay, so that's what we're going to use as the upper bound of our function from 0 to 0.7391. And when we plug this into our calculator, we get 0.400 something as the answer. Okay, number 3. We have the graph of 4x minus x squared. Okay, so that has an intercept at 0 and at 4, and has a maximum here at 2, 4. So this is the graph of 4x minus x squared, right? The y equals 0 about the x-axis. So here's our axis of rotation. Okay, no gaps. We're just figuring out what is the radius. So the radius is, right, the radius is your equation, right? The different heights are your equation. So this is a pi r squared circular graph from 0 to 4. Those are your intercepts. Okay, so those are your bounds of 4x minus x squared squared, because that's your radius. Your radius is found by taking the y value at any one of these points, at every single point. Right? There's an infinite amount of circles that we are adding up. Remember, volume is the integral of area. So our area is pi r squared. These are circles that we're adding up to find the volume. And the calculator says 107 as your volume when we rotate that area around your x-axis. Okay, we have a whole bunch of equations for this next one. We have this 6-degree polynomial. We have x equals 1, the x-axis and the y-axis, which makes me believe that maybe it's something in here-ish maybe, or 3. I'm not quite sure exactly what it looks like, but I know the bounds are from 0 to 1. Okay, and it's revolving around the x-axis, so that's a pi r squared integral. Okay, so that means I have pi on the outside from 0 to 1 of x squared plus 1 cubed quantity squared, right? So the radius comes from your function dx. So what happens when I square a cube? I get a 6, which looks like C will be the right answer. It has the right bounds, it has pi on the outside, and it has x to the 3rd quantity squared. Okay, the base of a loudspeaker is determined by 2 curves, x squared over 10 and negative x squared over 10 from 1 to 4. For this loudspeaker, the cross sections are square. So here is a cross-sectional volume. So the volume is the integral of x squared, right? Where x is the side of your square. Okay, so volume is the integral of area, and we have a whole bunch of squares that we're adding up. So the question is, how do I find the side length for my square? Right? If this is the side of my square, how can I calculate that? So we're going to calculate the whole side length by doubling the top half. Okay, because of the symmetry, the whole entire thing is twice the top part. So the side length is twice x squared over 10, which simplifies to x squared over 5. So this is the side length of my square. Okay, so when I do this integral, the volume is the accumulation of area. My side length is x squared over 5, and to make it a square, I have to multiply it by itself. And I'm going from 1 to 4. Right, that was my bounds here from 1 to 4. So whenever we're doing these cross-sectional area questions, you have to figure out, how do I represent the side of my shape that I can calculate for every value of x? My calculator says 8.184, which is, hey, there it is, 8.184. Very nicely done. Okay, number 6, a vase is shaped by shape obtained by revolving 2 plus sine x from 0 to 5 around the x-axis. Okay, so what does the graph of 2 plus sine x look like? Well, there's 2, right, when sine is 0. 1, 2, 3, 4, 5. We know sine has a curve like this, and then maybe it curves down like that. So maybe that's the curve. Right, so the vase, the vase, is going to come out to look something like this, right, when we rotate it. So we have a circular base, circular top. So does our area touch the axis of rotation? Yes, yes it does. The area of our base touches the axis of rotation. So volume is just pi r squared. And how do we find the radius of each of these things? The radius is just the y value. And the y value comes from our function. 2 plus sine x squared, pi r squared dx. And the answer comes out to be C, 80.115 cubic inches. Okay, what else do we got here? Okay, number 7 is a conceptual understanding. So let's look at the relationships. What is the relationship between G and F? F is the derivative of G, right? By the fact that it's an integral, by the fact that this is an integral means that F is the derivative of G, or G is the antiderivative of F. Okay, so here are so we have G as your function, and then F is the first derivative, so G prime equals F. So if we're looking at points of inflection, that's G double prime. What does G double prime equal? F prime. So here's the graph of F. We want to know, when is F prime equal to 0? Okay? And from our question, when do we have F prime equal to 0? It says it has a horizontal tangent at 2, which means the slope is 0, and it has a horizontal tangent at 5, which means the slope is 0. So where do we have points of inflection? At 2 and 5, right? So this is a conceptual understanding question. Do we know the relationship between G and its integral function? And yes, we do. G is the antiderivative of F, or F is the derivative of G. So the second derivative of G is the first derivative of F. Okay, number 8 doesn't need you to do much as long as we understand what area is. So area is the integral of your top function minus your bottom function, right, from certain bounds. So looking at our graph, notice we have 2 different sections where the top and the bottom are different, which means we're going to have 2 separate integrals in order to find their area. And D is the only one that has that option. So once again, no calculator here, just a conceptual understanding of what the area between two curves is. But number 9, this one we have to actually do some work. So the area is the integral from 0 to 1. So hopefully you know that these graphs cross at 1 and at 0. That's when root x equals x squared, when x is 0 and x equals 1. Of the top function, which is root x, minus the bottom function, which is x squared dx. Okay, so we have, this is basically x to the 1/2. So the antiderivative of x to the 1/2 is x to the 3/2 times 2/3 minus the antiderivative of x squared is x cubed over 3. So we're evaluating this from 0 to 1. Okay? And it turns out that this is, let's see, when we plug 1 into here, that gives you 2/3 minus, when we plug 1 into here, that's 1/3. And then when we plug 0 in, we get 0 and 0. So the answer is, what is 2/3 minus 1/3? That's 1/3. Very nice. Okay, number 10. The base of a solid is a region enclosed by y equals sine x and the x-axis on 0 to pi. So hopefully you know that on 0 to pi, sine has a positive graph. Right? Pi over 2, sine is 1. At pi, sine is 0. So there's the graph. So our base is the area right here. Okay? And we're making semicircles. Semicircles. So we're going to have semicircles drawn here and here and here. Okay? So first of all, what's the area of a semicircle?
It's
half of pi r squared, right? So that's the formula that we're dealing with in the first place. So volume is 1/2 of pi times the integral from 0 to pi of the radius of our semicircles squared. So let's go back. How do we find the radius of our semicircle? So remember, this is my semicircle. So what have I just drawn on the page?
the radius.
That's a diameter. That vertical blue line here is the diameter. So how do I find the radius? I take half of the diameter. So this distance here is my diameter. My radius is half of the diameter. And how do I find the diameter? Well, that's the sine of x. Right? That's the y value for each of these potential x's. So the radius of my semicircle is 1/2 of sine x. That's the hard part, is figuring out what my radius happens to be. 1/2 of sine x. So let's simplify this down.
When you square with the sine of x,
What is 1/2 sine x squared? What's 1/2 squared? That's 1/4, and sine squared is sine squared. So another constant is 1/4. I can bring my 1/4. What's 1/4 times 1/2? That's 1/8 pi from 0 to pi of sine squared. So which one of our options matches up? A, pi over 8, 0 to pi. A, 0 to pi of sine squared. And our final answer is A. The whole entire area is 1 and they're all equal. So each of these are 1/4 of the entire area. Okay, great job. Study, study. See you next time. Goodbye.